All right, recording is rolling. It is Tuesday, September 13th. A bunch of you guys just turned in the projectile quiz. So if you haven't yet, make sure you turn in here pretty soon. Now today, we're going to take today to do this spring scale lab. So I do need to get you guys set up with that, show you guys what's going on there. But before I do that, you guys have some new pages on your desk. All right, so one page looks like this. You guys see this page? So everybody pick up one of these. Back on your desk, right? You guys have this? So you guys got one per person? All right, so over the next few weeks, we're gonna be doing forces. I picked these 10 problems. I'm gonna have you guys turn in Friday, September 30th, which is about 2.5 weeks from now. Okay. All right, and then of course I need to show you guys like how to solve all these, so it's gonna take some time, but yeah, Friday, September 30th, I'll pick up those 10 problems from you guys. Okay. Not too bad there. Right, you guys also have a packet of conceptual questions. You guys see these conceptual questions? Okay, so get one of those. Now, this for you guys, honors, this is just an extra resource. I would like to do a Kahoot at some point over the next about 3 weeks that involves some of these conceptual questions. But these are all really solid questions. So there are 20 questions on each of Newton's 3 laws of motion for a total of 60 questions in this packet. In fact, on the back are written out Newton's laws of motion, right? First, second, and third laws. Look at there. Is that? Right, so yeah, next about 3 weeks, we're going to be doing forces and Newton's laws of motion. Okay. The other page you guys have, so everybody has one of those individually, right? Okay. The other page on your desk, you guys have one per group here. Looks like this. Okay. You guys see spring scales and some lab weights going on there. Looks like these spring scales, right? Guys, that. All right, so I'm going to take today to introduce forces. Now, all of forces is just a push or a pull. And these spring scales, they can measure like some amount of pull, right? Like if you pull on a spring scale, it's the spring stretches some amount, it tells you a force. And what's that unit, capital N? What does that stand for? Newtons. Yeah. So we're measuring forces in newtons. So I'm going to give you guys just some very brief notes here, just all these notes on just one page. Okay. So a force is a push or a pull, right? And you guys are right. It is measured in newtons. The symbol for that is capital N. Right, so we're going to have force as a variable measured in capital N is the unit, Newton. Right? Now, what is 1 Newton? Right? Because we haven't had too many variables and units going on so far. Right? There's been displacement in meters. There's been velocity meters per second. There's been time in seconds, and there's been acceleration meters per second squared. That's what we've been doing. Right? Mass is showing up here and there, but now mass is about to become a lot more important. Right? So 1 Newton, right, which is measure of force, breaks down. This is a composite unit. I'll tell you guys exactly what it is. It's 1 kilogram meter per second squared. Okay, that's what a Newton is. So every time you push on something or pull on something, so if I'm like pushing this around, right, applying a force, okay, I could quantify how hard I'm pushing in a unit that breaks down to kilogram meter per second squared. Now, at a glance, that might not immediately make sense. It's like, wait, what? Right. But if you pair that with Newton's second law of motion, which is on the back of this packet, right? So look at Newton's second law of motion here. I bet you guys even know Newton's second law of motion, maybe from like middle school. You guys remember like F equals ma, right? Force equals mass times acceleration, right? Or I'm going to rearrange this. There's a way I like to use this too, which is acceleration is caused by a force acting on a mass. Okay. It's really a net force. So put a little subscript net, like a net force. Okay. So what this says, and see these 2 lines are the same, they're just algebraically rearranged versions of this, right? Is that if you put a force on a mass, it will cause it to accelerate, right? Force per unit mass is some acceleration. Okay, so if I push this with some force, it's going to cause it to like speed up, right? That's what acceleration is, right? It's like changing your motion, like speeding up or slowing down, right? All right, and it looks like the more force, the more acceleration, and the more mass, the less acceleration. There's an inverse relationship between mass and acceleration. You guys see that too? Okay. Now let's go back and look at those units, because the reason I'm putting Newton's second law of motion up here at all is just to show you guys how it matches with the units. So you guys know force is going to be measured in newtons. That's exactly what it says on the spring scale. You guys just told me that. Okay. Hey, mass is measured in kilograms, and acceleration, hey, that's in meters per second squared. You guys see how this Newton's second law of motion will directly tell you what 1 Newton is? Okay, guys, all right, so we're good so far. Okay. Now the purpose of this lab, now this lab is really a 10 mini labs. It's like 10 mini activities. Is I want you guys to get your hands on the spring scales and the lab weights and see how exactly does force distribute. Like when I make say like I make this chain gang here, what are the force ratings on each one of these scales? Or what if I make like this Y shape and I start spreading it out, right? How does force distribute throughout that system? Right? And then there's some on the back too, right? And what if I accelerate this thing up and down or drag it across the surface, right? So we've got 10 mini labs going on. Right? But you know what's helpful to know is how your tool works, right? Because there's definitely a spring here, right? Something to do with the spring. So I'm going to introduce another idea to you guys today, which is called Hooke's law. So next notes, just going to fit down this space right here and say Hooke's law. Okay. Now Hooke's law has to do with ideal springs. So just springs. So if you put a force on a spring, what does that cause it to do? Okay. So let's say I have like an unstretched spring, and it's just that's like a picture of a spring, right? Okay, it's unstretched, which means there's no forces on it. It's just like hanging out, right? Okay. Now, what if I put a stretching force on it? Stretch. Okay. So I could put a pulling force here and a pulling force here. I'll label this F force and F force, right? And if you think about it, if you're thinking a step ahead, these really have to be equal and opposite forces. They have to be the same value if this whole thing is in equilibrium. Okay. And that actually ties to Newton's third law of motion, right? Which I'm sure you guys could have said before you ever walked in this classroom. For every force, there's an equal and opposite reactive force. Right? That's what I just drew right there, right? Okay, so we got equal and opposite force pair going on. Okay. And how much is this going to stretch? How much? I will label this X. Some textbooks do delta X. I'll just call that X. I like to stretch them out. Okay. And what Hooke's law says, there's a nice tidy formula right here. It goes like this. F, so that force, equal and opposite force pair, is equal to K times X, right? Where F is the force that you applied. Now, here I'm showing it stretch, and the spring scales that you guys get, you can only ever stretch these. But there are some situations you might have a spring you could also compress, and this would work the same way. So this could also apply there. Okay. So X is how much stretch. Okay. Or in some situations, compress. So I'll say or compress, just to generalize it. Okay. And then what's the deal with this K? Well, do you guys see how there are different colored spring scales up here? Okay. Now these different colored spring scales correspond to different types of springs. My favorite ones are the brown ones because they're kind of like the middle stiffness. They're the most versatile. This is the only one I have here today. The other ones are being borrowed, but here, let's go to these. Right, so I put some force and it stretches some out. Okay. Right. I also know that the newtons are scaled linearly. So it goes 0, 2, 4, 6, 8, 10 newtons. This brown scale can read up to 10 newtons of force. Okay. Which, by the way, is extremely close to 1 kilogram mass. If you hang it, it's extremely close to 10 newtons. So wait, it's like 9.8 newtons. So a lot of times you just round it to 10 newtons. Okay. But when you get your hands on some of these other scales, just one thing I want you guys to do today, say, ooh, this red one's a little stiffer. It's like twice as stiff. It goes up to 20 newtons. The white one goes up to 30 newtons. Ooh, man, I can really feel it. It takes a lot of force to stretch that. And the blue one, this goes up to 2.5. Oh, that's hardly anything at all. Right, it's really easy to stretch that to a little tiny force, and it's like stretches no problem. Is it? Right, so if I rank order these, it goes like blue, then brown, then red, then the stiffest one is the white one. Right? Okay. Hey, that's what that K refers to. This could be spring. You can call it the spring constant, right? Or sometimes you'll see it stiffness. Right? Like how stiff is the spring, right? And each of these spring scales has like a different spring constant. Right? Let's look at the units real fast. The units that would pair up with this this formula. Because you guys know force is measured in newtons, right? Which breaks down to this. Okay? X, oh, that could be like some number of centimeters or more generally some number of meters, right? Right. And if I'm putting this together, right? Here's the kind of challenge question where this all comes together. What do you guys think the unit is to quantify how stiff the spring is? Right? Like if I want to say this spring is stiffer than the spring, like, okay, can you quantify that? Oh, okay, maybe I could figure out a number to it, tag a number to it, and say what's the units on that number? What unit goes right in these set of parentheses? Guys remember doing like a unit analysis, dimensional analysis, like first week of school? Right. What's going to tie meters to, how do you convert meters to newtons? How about newtons per meter? Ah, can that describe some spring stiffness? Right. So yes. So if you had a spring, let's say you stretched it by like make up crazy numbers here. Let's say you stretch it 2 meters, and to do that, it takes like 500 newtons. So 500 newtons to stretch 2 meters. I'll divide the 2 down, and that would be what, 250 newtons per meter, right? And that could quantify how stiff the spring is. You guys get that? All right. Any questions so far? Okay. All right. So about to get you guys rolling here. I just want to mention a couple little details just to knock out some questions that I always get on this lab. Okay. Remember, there's 10 mini labs going on here. On the very first one, see where there's just the very first one's the most straightforward. All I want you guys to do is just put a lab weight like right here, just hook it, right, and then get the reading, and then switch out different lab weights. So treat on the first one, treat mass as an independent variable. That's to say you're going to use different masses, right? I'm going to have you guys do a small graph right here. So as you're increasing mass, I bet you guys probably have a pretty good guess what that graph's going to look like, but I'll leave it to you to make the measurements and actually plot that out, right? But you're going to use different masses, right? In contrast to that, the second one, you guys see there's 2 spring scales? Okay, can you guys hang like 2 spring scales like this? Right. See where I labeled the same mass? Just use the same mass over and over. Right. See, I've got 2 spring scales hanging, and there's one. Don't use those same. Just I don't have a lab mass up here. Okay, but they're all back in lab tables. Okay. Can you guys? Hey, you know how if you stand on 2 feet, you can like shift your weight around and put like more weight on one leg or the other leg? Okay. This is like that, except it's in tension instead of compression. Right? Can you like shift these around so that one of these might carry more weight than the other? Right? And suppose you had like a 1 kilogram lab mass, which is extremely close to 10 newtons of weight. Right? Do you think it might split possibly 5 and 5? And what if one of these is reading like 3 newtons? What do you think the other one's reading? 7. Big 7? Ooh, I like that hypothesis. I'm gonna have you guys actually do the get some empirical evidence, see if that's true. That's a good hypothesis. Okay. Got you guys spreading it out here, like making a Y shape. As you spread out this Y, make it closer to a T. What happens if you have a chain gang going on here? How does the force distribute throughout that? If you accelerate it up and down. Yeah, if you do these different activities, what happens to the force readings? All right, so now I think you guys are about ready to head back there. So any last questions before you guys go back? All right, so I will walk around, help you guys out. And yeah, we're doing this for the rest of today. You guys turn in your projectile quiz.